Hi folks, welcome back to Physics with Captain Rod. Making this video here to help you understand how equivalent resistances are calculated in both series and parallel. So I'm going to start with a series circuit. So this circuit right here, that's an example of a series circuit. And the defining characteristic here, first of all, let me close the switch here. So we're going to close the switch. The defining characteristic of a series circuit is that the current will be the same through these two resistors, or through these two light bulbs. In our picture here, our current is going to be this way, assuming positive charge carriers. So the first thing we're going to talk about here is the circuit diagram. So the resistors here, or I'm sorry, the bulbs that I labeled like 1 and 2, no matter what these are, light bulbs or whatever electrical devices they are, maybe they're actual resistors, they're going to have a certain resistance here. So I've called the resistance of the first bulb R1, second bulb R2. And I'm going to go ahead and also, like I like to do with all circuits, color code the potentials. So in red, the high potential side of our circuit, whoops, try this again, in red is here. And this is all constant potential because in theory, right, this is all wire made of conducting material. And remember from my IFAX video, right, conductors themselves are an equipotential. Right, we will get a voltage drop across the resistor. So this is going to be a different voltage. And then I'll just leave this one black as that's another constant potential. The delta V here, of course, is representing the voltage on the battery. Now, the idea here is we want to be able to find a single resistor that is mathematically equivalent to this pair. Now, hopefully your gut will tell you how this is done when they're in series. As you add resistors, hopefully we realize that that probably would add to resistance. But we're going to talk about like mathematically how does this work out. So you notice this red to black. If we walk across this circuit and we go black to yellow, that's a voltage, and then or black to orange, and then orange to red, that's another voltage, and that's the same as going over here, black to red. So our voltage here, I'm going to call it delta V, is equal to the voltage across this. I'm just going to call that voltage 1 plus the voltage across this, voltage 2. And by Ohm's law, this voltage can be written IR equivalent because our current, I'll draw this in blue, would be this way in this picture. Over here, that's this. And that voltage right here is equal to the voltage across here, IR equivalent. And then that's going to equal, right, when we apply Ohm's law here, IR1 and the, and the voltage across here, so plus IR2. And this is a series circuit. The currents are all the same. You can put an ammeter here, 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 anywhere in the circuit, you're going to get the same value. So those currents divide out. And we get, well, R equivalent is equal to R1 plus R2. And had we had a third resistor, you would just put plus R3 and so forth. This can kind of go on and on and on for any number of resistors that you want to add to this. All right, so let's talk about a parallel combination now. So here is a picture of two bulbs wired in parallel. And again, I'm going to color code the potential. Well, first of all, I'm going to close the switch in my picture, okay? And now color code the potential again. The high potential side of the circuit is here. This is all equipotential because this is all conducting material to here. Now in theory, there's a voltage drop across the light bulb, and I'll just leave this color what it is. Again, if I come over to this picture, this, by the way, would be the circuit diagram for my picture on the left. Again, all equipotential because it's all conducting material. I'll just leave the other side black. I guess since this is done too, let's do this. We'll blacken this up so that they match. There we go. All right, now you'll notice here that the delta V for the battery, right? Red to black, and look at the resistors, red to black, red to black. That's the defining characteristic for a parallel combination, is the voltages are the same. Now this problem has three currents now. I'm going to draw them like current 1. And whatever current 1 is, it would be, ammeter wise the same here, 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 anywhere in that branch. But what happens is there's kind of a divvying right here. Some of that current ends up going this way, some of it through this resistor. I'm going to call these like I1 and I2. Oh, I see I already called this I1. You know, I'm going to go back and change this to just I. I might as well keep the 1 in the resistor 1 and the I2 in the resistor 2 kind of equivalent. All right, now math-wise, right, when we look at this junction, whatever goes in must come out. So that means that this current I is equal to the sum of what I called, I1 and I2. Now, probably should have talked about the picture on the right. The idea behind equivalent resistance is what single resistor can I find that's mathematically equivalent to this pair? Right. And we're going to start with this. The current coming into this junction here is equal to the sum of these two. And remember Ohm's laws, voltage equals current times resistance. So current can be expressed as voltage over resistance. So the current, this one, which in this picture is here, can be expressed as the voltage divided by R equivalent. Because here's our voltage, and this should be a delta V. That's how it's labeled right here. Delta V. And, all right, equals, right, I1, again, we can write as the voltage across this divided by R1. And I2 can be expressed as the voltage across here divided by R2. And you'll notice I'm writing all of these as delta V's up top. And that's because look at the picture. This delta V is the red to black. And then look at the resistors, red to black, red to black. Again, that's the defining characteristic of a parallel circuit. So these voltages are all the same and therefore cancel out. So we can write 1 over R equivalent is equal to 1 over R1 plus 1 over R2. If we had a third here, like in this circuit, an R3, then we would have a plus 1 over R3. I'm just going to add a plus dot 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 for as many as you care to put in parallel. So there's a little bit about the history of the mathematics, I guess, if you will, of how equivalent resistances are calculated and why these equations look the way they do here. So that's how resistors in series are calculated, the equivalent resistance of a series combination, I should say, and this is how the equivalent resistance of a parallel combination of resistors are calculated. I hope that this video has adequately explained that for you. Have a great day.